In this video, we will create the basic game framework using both structures and enumerations. We will begin by creating the library. In order to do so, we will add the header file first. We will give the name to the header file. Both the header file and the implementation file must have the same name, but differ only in their extensions. We will use the standard file name _h for the guard conditions. We will now add the implementation file. As stated previously, it will have exactly the same name as the header file, but will end with the CPP extension. We will add all of the files to the active projects and link the header file to the CPP file by including the header file from within the CPP file. In order to make use of the library from within the main.cpp file, it will be necessary to hash include the header file from within the CPP file. Because adding the header file and CPP file changed the project structure, it will be necessary to say yes when prompted to save the project if you close code blocks. This is always a good idea. In order to add all of the constants and function prototypes to the namespace, inside the header space we will use the namespace gamespace. Likewise, inside the implementation file, we will need to use the same namespace specification so that everything is grouped together in terms of name. In order to make use of these names inside main, we will have to use the using namespace command in order to bring all the names into the current namespace. We will now begin implementing the game itself, starting with the game world structure. We will use type definitions to simplify the definition of the game array. A single row within the array is an array of integers, while the game array itself is an array of game rows. All of the state of the game will be encapsulated with a single structure called game world. The game array itself, along with its length and the position of the player, will all be stored within this single structure. We will now consider the first milestone within game development, namely the creation of the game world, its initialization, deallocation, and display. All of the possible kinds of entities which can exist within the game array will be defined using an enumeration, namely empty space, the player, and the goal. The game world creation function will return a correctly allocated and initialized instance of the game world structure when given the number of rows and number of columns as input. Display function, which we are calling show world, will only need to take the instance of the game world structure as its input. Since it doesn't make any changes, it will not need to take this as reference. It does not return anything and is therefore a void function. The deallocation function, which we are calling free world, will however need to take its parameter by reference, as it will need to set the internal array world pointer to null pointer. The following system libraries will be needed within our own, namely cstandardlib for system exit and rand, followed by iostream needed for cin, cout, and cir, and lastly ststream, which gives us the string stream used by our conversion function. We will naturally also be using the standard namespace. The createWorld function will naturally instantiate and return a GameWorld instance. We will begin by storing the number of rows and columns within the structure. We will now allocate memory for the outermost level of the GameWorld array. This array will be as large as the number of rows within the game. Once that is complete, it will now be time to allocate the inner row arrays, which will store the actual entities within the game. Needless to say, there are as many of these as there are rows within the game. Also, it is worth noting that a single row is as large as the number of columns within the game. We can now loop over each row array and set its contents to be empty space. We do not just want a game world that is filled with empty space. We would like to distribute obstacles randomly throughout the environment. In order to do so, we will need a helper function, namely the ranged random function. In order to generate random numbers, the main function will need to be modified so that it can set the seed for the random number generator. This will require the cstandardlib and ctimelib inside main, as well as a call to srand using the output of the time function, giving the number of seconds which have passed since the 1st of January 1980. The ranged random function will give us back an integer as its answer, and will need to take in two integers as its input, namely the minimum and maximum value within the range of random numbers we would like to generate. The number of possible random numbers which could be generated may be calculated by taking the maximum and subtracting the minimum, then offsetting that by 1. Once we call the rand function, we will get a random value between 0 and some large maximum. We will need to wrap this around our range using the modulo operator, but this will give us a result that will definitely start at 0. In order to correct this, we will need to add the minimum to this result to offset it by our desired amount. Our ranged random function may now be used to position the goal within the environment. This can be done by generating a random row and random column for it in the ranges 0 to rows -1 and 0 to cols -1 respectively. The same strategy may be used to position the player within the environment by generating a random row and random col value for the player in the ranges described previously. The player's row and player's column naturally are stored within the structure. However, because we do not wish the player to start on top of the goal, we will need to take extra precautions to make sure that the row and column component of the goal and player are not simultaneously exactly the same. This is done using a while loop to repeatedly regenerate the player's position if necessary. Now that the player's row and column do not conflict with the goal row and column, we can safely place the goal within the environmental array. We can now begin implementing the free world function, whose purpose is to deallocate the game world array, as well as to set the array pointer to null. Because it is an invalid operation to free an already freed array, we will need to ensure that the array is not already null before proceeding. This can be done quite nicely using assertions. In order to do so, we will include the CSCO1A1 library. Because assertions are typically disabled in the final release version of a program, they are not suitable for handling user errors and are rather used to handle programmer errors. Assertions may be disabled by defining the ndebug macro prior to hash including the header file for the CSCO1A1 library. In order to free the inner row arrays, it is first necessary to loop over every row and free that inner row array first using delete with square brackets. Once that is done, the outer array world array may be deleted and the pointer set to null. We will now begin implementing the display function showWorld. In order to simplify the creation of the showWorld function, we will be using a constant array of characters which will store the ASCII symbols for every game world entity. However, the order in which these symbols are defined is very important, as it must exactly match the entries within the enumeration defining the game world entities. This is because we will use those values in order to index the array during the showWorld function. In order to display the world, it will be necessary to loop over all possible rows and columns. Once we have reached the same position as the player row and player column, we can output the player symbol. If this is not the case, we can inspect the array world and use the value stored there as an index into the array of symbols and output the appropriate symbol. We then output a space to create a nice visual effect, and at the end of every row we output an end of line. We have created our world creation function, display function, and destruction function. We can test them by updating main. In order to add some dynamism to our program, we will use command line arguments to capture the number of rows and number of columns. In order to capture the command line arguments, we will need to make use of the overloaded version of main. argc represents the count of the command line arguments, whereas argv represents their values. argv is a one-dimensional array of C strings or a two-dimensional array of characters which has the same meaning. Because command line arguments come from outside the program, it is necessary to validate the input. In order to do so, we will write a conversion function. This may result in failure, which is why we need to establish an enumeration of status codes, including success at value 0 and error codes at all non-zero values. The conversion function will take in as its input a string and return an integer version of that string. Because the string parameter of the conversion function forms part of the external API for the library, it will be necessary to include the string library inside the header file, as well as using the standard namespace to make sure the name resolves. It is normally not considered good practice to use the standard namespace wholly inside a header file, however we will do so for the sake of simplicity. In general practice, one would rather use the scope resolution operator prefixed by std in front of the string's name in order to resolve it. The conversion function will operate as follows. We will use the string streams ability to convert from string to integer in order to do the heavy lifting for us. We will also use its ability to check for a fail state should conversion not be successful in order to handle any errors that may come in through user input. The program expects as its arguments the number of rows and number of columns. We should test to see that the correct number of command line arguments have been passed using argc. Since argv at position 0 is always occupied by the name of the program, argv at positions 1 and 2 will take the values of rows and columns respectively. This brings our total count of arguments to 3. Now that we have ensured that there's the correct number of command line arguments, we can use the conversion function we wrote earlier in order to convert argv at position 1 and argv at position 2 respectively. Since we have not specified any command line arguments as part of the project settings, running the program will produce an error. We can set these values inside the Set Program Arguments option in order to prevent us from having to run the program from the command line each time. It is worth noting that this will have the effect of changing the project's configuration, and therefore we should say yes when we save the project upon closing code blocks. It is good to do this at any point in time in which you may change the project, such as adding new files, changing build options, or setting program arguments. We will now wish to add rocks to the environment. This will require a few changes to some of the things we've written already. For example, we will need to add a new entry to the enumeration for game entities to represent rocks, and at the corresponding position inside the array of symbols, we will need to pick a character to represent rocks. The rock chance constant represents the percentage likelihood of a rock occurring in the environment during initialization. This will be used by generating a percentage, a number from 1 to 100, and checking to see if it falls in the interval 1 to rock chance inclusive. If this occurs, we will add a rock to the environment by simply placing the corresponding value within the world array. Alternatively, should this not occur, we will simply add a space to the environment as before. Now that we have rocks in the environment, it is important to ensure that the player is not instantiated on top of a rock. This can be done by checking to see what exists in the player row, player column position of the world array while placing the player. This can be included inside the while loop and regenerate the player's position should it fail this test, in addition to the previous one, preventing it conflicting with the goal location. A game world which is too small or too big cannot be used, so we will create a helper function which will enforce the range of the rows and columns and raise an appropriate error message should the maximum or minimum be exceeded. We will then use this inside main to make sure that the rows and columns we've received from the user make sense. The next major milestone within the game will be to allow the user to perform in-game actions. It will require a fair amount of code to be written, as well as modifications to main to introduce a menuing system to allow users to select the action they wish to perform. These actions are normally movement related, but do not have to be. The action enumeration will store all possible actions the player may perform, in this case, namely the directions of motion. The perform action function will take in the world record as one of its parameters, along with an instance of the action enumeration. The world record must be passed by reference because various members will change, namely the player row and player column. Our first duty within perform action will be to find the player within the environment. However, since we are storing the player within the structure, we do not need a dedicated find player function. It is also important to introduce an assertion to make sure that the array has been allocated. This is necessary because we will be using the array within this function. It will now be necessary to determine where the player is going, represented by the variables target row and target column, which default to the player's row and player's column. In the case of non-movement related actions, this is quite important. We will then use the incoming action enumeration to determine how to modify the target row and target column to find out where the player ends up. Once we have determined the player's target row and target column, we need to consider the fact that not all target rows and target columns are valid coordinates within the game world. In order to address this, we will need to create a helper function to test if a given pair of coordinates are within the game world. A given coordinate is within the game world if its row value or column value is not less than 0, nor is it too big, namely greater than or equal to rows or columns respectively. In such cases, the function must return false. Should all of these tests be passed, however, the function will return true to signify that those coordinates are in the game world. It makes no statement about what is located at that position in the game world, however. With this helper function completed, we can now test the validity of the target row and target column generated by the previous switch statement. Now that we know that those coordinates are valid, we can safely access the array to determine the effect of the previous action. By looking inside the array, we can see if the destination is an empty space, in which case we update the structure's player row and player column data members to move the player. Otherwise, we check to see if it's a goal, and in which case end the game with the player winning. We do not need to explicitly test for moving into a rock, because that will have no effect, and simply leave it out of the logic. Now that the perform action function is completed, we now need to update main to allow those actions to be selected by the user. As is customary, the menuing system will be governed by a do-while loop, since the initial state of the world and possible actions will need to be presented to the user at least once, even if they choose to immediately exit the game. The first action undertaken by the loop will be to clear the screen, followed by displaying the initial state of the world, and then prompting the user for the possible actions they may wish to perform. Now that the user has their possible actions presented to them, we will capture their selection using the standard input stream. We will use a character to store their action, because the conversion from keyboard character to normal character is not likely to produce an error. In fact, it can't. This will avoid us having to test the standard input stream for a failure state. We will use a switch statement to handle the user's action. We will use the fall-through behavior of the case statements to handle both upper and lowercase versions of the character. We could instead convert the character to uppercase beforehand. However, this is left as a reminder of the fall-through behavior, which is often a gotcha that catches programmers who aren't used to it out. We will call the perform action function with an appropriate parameter representing the direction for each of the cases corresponding to a movement action. Exiting the menuing system is handled by modifying the loop control variable blnContinue to be false, thereby ending the do-while loop. We will use the default case of the switch statement to handle any input from the user that does not correspond to one of the action types they were prompted with. Because this is not a very serious kind of error, we will simply inform the user and allow them to reselect. With the movement function completed, the game is now complete. We will now compile the game and play it in order to test it. We do advise, however, that you compile and test your code regularly throughout the process, not just at the end of milestone 1 and at the end of the actual game entire. This will allow you to capture any errors earlier and deal with them. I hope that you have found this tutorial to be useful and wish you the best of luck for both your second semester test and your examination.